On a routine Tuesday morning in 2025, passengers boarding Swiss International Airlines flight LX8 had no idea they were about to make history. The fuel powering their aircraft wasn't pumped from the ground, it was made from the air around them. Welcome back to Curiosity AI. I'm your host, and today we're diving into one of the most ambitious engineering projects on Earth, turning atmospheric CO2 into jet fuel. The aviation industry has a problem that batteries can't solve. You simply cannot put enough lithium-ion cells in a Boeing 777 to fly 8,000 miles across the Pacific. The physics don't work. The weight penalty is too severe. But what if instead of replacing jet fuel, we could make it differently? What if we could create chemically identical aviation fuel using nothing but air, water, and renewable electricity? That's exactly what companies like Climeworks, 12, and Infinium are doing right now. They're building industrial facilities that capture CO2 directly from the atmosphere and transform it into synthetic jet fuel that works in any existing aircraft engine. Today we'll explore how this impossible-sounding technology actually works, which companies are scaling it to commercial production, and whether it represents a realistic pathway to carbon-neutral aviation or an expensive distraction from better climate solutions. Let me walk you through how you turn air into jet fuel. The process involves 4 main steps, each presenting unique engineering challenges. First, you need to capture CO2 from ambient air. This is harder than it sounds because atmospheric CO2 exists at just 420 parts per million. That's like finding a specific grain of sand on a beach. You're processing enormous volumes of air to extract meaningful quantities of CO2. Climeworks operates the world's largest direct air capture facility in Iceland called Mammoth. It uses giant fans to pull air through solid sorbent materials that selectively grab CO2 molecules. The facility can capture 36,000 tons of CO2 annually, though early operational experience has shown the challenges of keeping these systems running reliably at scale. The second step is producing green hydrogen by splitting water using renewable electricity. This isn't new technology, but the scale required for e-fuel production is staggering. Advanced electrolysis systems from companies like Topsoe can achieve better efficiency than conventional methods, but you're still talking about massive electricity consumption. Third, you convert the captured CO2 into carbon monoxide through high-temperature chemical reactions. This step alone requires significant energy input, which is why the overall process is so electricity-intensive. Finally, you combine the carbon monoxide with hydrogen through Fischer-Tropsch synthesis to create synthetic hydrocarbons. These must then be refined to meet strict aviation fuel specifications. The result is drop-in compatible fuel that meets the same ASTM standards as conventional jet fuel. When Swiss Air operated that historic flight, they were burning fuel that was chemically identical to petroleum-based jet fuel, just made through an entirely different process. Several companies have moved beyond laboratory demonstrations to commercial-scale production. Let me introduce you to the key players. 12, formerly called Opus 12, has achieved something remarkable. Their E-Jet sustainable aviation fuel has received full ASTM certification and is already being used by United Airlines, Alaska Airlines, and the U.S. Air Force. This isn't a prototype or demonstration fuel. It's operational, certified aviation fuel being used for real flights. Infinium is taking a different approach focused on massive scale. Their Project Roadrunner facility in Texas is designed to be the world's largest e-fuels plant at startup, capable of producing millions of gallons annually. The project has attracted backing from major infrastructure investor Brookfield, suggesting institutional confidence in commercial viability. Synhelion demonstrated yet another technological pathway. Instead of using electricity to drive fuel synthesis, they use concentrated solar power to create the high temperatures needed for thermochemical reactions. Their solar fuel powered the Swiss Air flight that made headlines in 2025. GIF Global has been pioneering e-fuel production in Chile's Patagonia region, taking advantage of abundant wind resources. Their Haru Oni facility produces synthetic gasoline and kerosene with backing from Porsche and Shell. In 2025, they began integrating direct air capture units to increase atmospheric CO2 content in their feedstock. On the CO2 supply side, Occidental's STRATOS facility in Texas represents the next major test for direct air capture scaling. Designed to capture 500,000 tons of CO2 annually, it's more than 10 times larger than Climeworks Mammoth facility. If STRATOS operates successfully, it could prove that DAC technology can reach the industrial scale necessary for widespread e-fuel production. Now let's talk about the economics, because this is where things get challenging. Current direct air capture costs range from $600 to $1,000 per ton of CO2, based on real operational data from existing facilities. Companies project these costs could fall to $100 to $250 per ton with technological improvements and scale, but we're not there yet. The complete e-fuel production process requires approximately 20 to 30 kilowatt-hours of electricity per liter of synthetic jet fuel. To put that in perspective, that's enough electricity to power an average home for about a day, just to produce 1 liter of fuel. This translates to current production costs of roughly €3 per liter, compared to about 50 cents per liter for conventional jet fuel. Without subsidies, airlines simply cannot afford synthetic fuel at these prices. Here's where policy becomes crucial. The European Union's Refuel EU aviation mandate requires airlines to use sustainable aviation fuel starting with 2% in 2025, ramping to 35% by 2050. More importantly, there's a specific requirement for synthetic e-fuels, at least 1.2% by 2030, jumping to 35% by 2050. This creates guaranteed demand regardless of cost. Airlines will be forced to purchase e-fuels even at premium prices, providing the market certainty necessary for large-scale facility investment. In the United States, 2 tax credits are improving project economics. The 45Q credit provides up to $180 per ton for captured CO2, while the new 45Z clean fuel credit offers up to $1.75 per gallon for sustainable aviation fuel based on carbon intensity. These subsidies can substantially improve project economics, potentially making e-fuels cost competitive with conventional alternatives when combined with EU mandates. This brings us to perhaps the most important question about e-fuel technology. Is this the best use of renewable electricity? Every kilowatt-hour used to produce synthetic fuel is electricity that could directly replace fossil fuel consumption elsewhere. The energy penalty for e-fuels is substantial. You could electrify significantly more ground transportation or industrial processes with the same renewable electricity needed for modest e-fuel production. Critics argue that the 5 to 6 times energy penalty compared to direct electrification makes e-fuels an inefficient use of scarce renewable resources. Why produce synthetic jet fuel when that same electricity could eliminate coal power generation or electrify freight transportation? Supporters counter that aviation represents a hard-to-abate sector where few practical alternatives exist for long-haul flights. Battery technology may eventually work for short regional flights, but intercontinental aviation will likely require liquid fuels for decades to come. The question becomes whether society should prioritize energy efficiency or focus renewable electricity on sectors where no other decarbonization options exist. There's also the timing consideration. E-fuel production can potentially provide grid stability services by consuming excess renewable generation during periods of high wind or solar output. This could improve the overall economics of renewable energy deployment while providing productive use for electricity that might otherwise be curtailed. Looking ahead to 2030, the industry faces unprecedented scaling challenges. Meeting even the EU's modest 1.2% e-kerosene target would require approximately 3.6 million tons of synthetic fuel annually. That's roughly 100 times current global production capacity. Projects like Norsk e-fuel in Norway, planning 50 million liters per year, and multiple facilities from Infinium could contribute to meeting this demand. But most remain in development phases with significant technical and financial risks. The operational performance of facilities like Occidental STRATOS will be crucial. If large-scale DAC proves reliable and costs decline as projected, e-fuels could achieve commercial viability by the mid-2030s. However, this timeline depends on continued technology improvements, access to cheap renewable electricity, and sustained policy support through multiple political cycles. The industry also faces infrastructure challenges beyond fuel production. Distributing synthetic fuel to airports worldwide, ensuring quality consistency, and maintaining supply chain reliability will require significant coordination and investment. Perhaps most critically, achieving meaningful scale would require renewable electricity deployment far beyond current global installation rates. Producing just 10% of global aviation fuel synthetically would need approximately 1,500 terawatt-hours of additional renewable electricity annually. That's roughly equivalent to all current wind power generation worldwide. Direct air capture e-fuels represent one of the few pathways available for decarbonizing long-haul aviation using existing aircraft technology. Swiss Air's historic flight proves the concept works in practice. Companies are building commercial facilities, and policies are creating guaranteed demand. But enormous challenges remain. Current costs are prohibitive without subsidies, energy requirements are massive, and scaling to meaningful impact would require unprecedented renewable energy deployment. The technology may prove most valuable for specific applications, rather than wholesale replacement of conventional aviation fuel. Premium routes, corporate sustainability programs, or regions with abundant renewable resources could adopt e-fuels while the broader aviation sector pursues other solutions. The next 5 years will be critical. If facilities like STRATOS operate successfully and costs decline as projected, DAC e-fuels could become a cornerstone of aviation decarbonization. If technical challenges prove intractable or energy costs remain prohibitive, the technology may remain limited to niche applications. Ultimately, the bet on turning air into jet fuel represents a broader wager on humanity's ability to engineer solutions to climate change through advanced technology and massive industrial deployment. Whether that bet pays off will depend on factors ranging from electrolyzer efficiency improvements to geopolitical support for renewable energy development. For aviation, it may be the best option available for maintaining global connectivity while addressing climate change. That's a wrap on today's episode. What do you think about using renewable electricity for synthetic fuels versus direct applications? Join the conversation in our community, and I'll see you next time on Curiosity AI.